In this lab, we will explore pulse width modulation, PWM, and how it helps us control devices like LEDs or motors. We'll focus on two key components of PWM, duty cycle and frequency. PWM simulates an analog signal using digital signals. It switches a signal on and off very quickly. By adjusting how long the signal stays on versus off, we can control the amount of power delivered to a device like an LED. The duty cycle is the percentage of one complete cycle during which the signal is on. A 50% duty cycle means the signal is on half the time and off the other half. If we increase the duty cycle to 75%, the signal stays on longer, making the LED brighter. Now let's talk about frequency. Frequency is how many times the signal repeats per second, measured in hertz. A higher frequency means the signal switches on and off more times per second. This is an example of a digital signal we might produce on a Raspberry Pi. The digital signal is shown in red, and the blue lines represent increments of time. On the bottom axis, we have three labels, 0, 1, and 2. The numbers 1 and 2 represent seconds. At the 1 second mark, you can see the digital signal drops to 0 volts. Between 0 and 1 second, there are 9 divisions representing tenths of a second. Notice the slightly larger line halfway between 0 and 1. That represents a half a second. At a half a second, the signal moves from 0 volts to 3.3 volts, or from an off state to an on state. For this specific signal, the time between 0 and 0.5 seconds is off time, and the time from 0.5 to 1 second is on time. When we combine the off time and the on time, we get 1 full second. This 1 second time frame is known as a cycle. We measure cycles in hertz. 1 hertz equals 1 cycle per second. The combination of on and off times in this signal is also called the frequency. The frequency refers to how many cycles occur each second. Hertz is how we measure the frequency, or how often the event happens over time. Later we'll look at how changes in frequency affect our LED. For now we're keeping the signal at 1 hertz. The next term we need to define is duty cycle. The duty cycle represents how long the signal stays high, or the percentage of time the signal is on during one cycle. In this example, the signal is off for half the time and on for half the time, meaning this signal has a 50% duty cycle. To ensure we fully understand duty cycle, let's look at two more examples. In the first we have 50% duty cycle, meaning the signal is on for half the cycle. The second example shows a 25% duty cycle, meaning that the signal is on for only a quarter of the cycle. Finally, we have 75% duty cycle, meaning the signal is on for 3/4 of the cycle. If the signal remains on for the entire cycle, that's called a 100% duty cycle. A digital signal with a 100% duty cycle would result in a constant 3.3 volts, or whatever the source voltage is. At a 50% duty cycle, a digital circuit with a 3.3 volt source voltage would average 1.65 volts over time. Half the time the circuit is on and half the time it's off. At a 25% duty cycle, the average voltage would be around 0.825 volts. At a 75% duty cycle, the average voltage would be around 2.48 volts. It's important to note that we're not actually changing the source voltage to these values. Instead, the signal switches rapidly between 0 and 3.3 volts. This switching happens so quickly that most multimeters will register the average voltage over the cycle. So in this case, the multimeter would show a value switching between 0 to 3.3 volts within 1 second, but might average out to 1.65 volts. If we connect our LED to a circuit with a 50% duty cycle at 1 Hz, meaning 1 cycle per second, we would likely see the LED blink. Half the time the LED would be off and half the time it would be on. That half a second interval would be visible to the naked eye. The multimeter may also detect this variation. To reduce the flickering visible to our eyes, we need to increase the number of cycles per second. The chart on the left shows an example where we increase the cycles per second to 2. With this change, the LED is off for a quarter of a second, on for a quarter of a second, off again for a quarter, and then on again. The duty cycle is still 50%, meaning the LED is on for half the time and off for the other half. However, we're now running 2 cycles per second instead of 1. You would still likely see the LED blink at 2 Hz. So, we would need to increase the frequency to something like 50 Hz to make the flickering imperceptible. The duty cycle remains the same, but the number of cycles per second increases. In our next lab, we'll use an LED and a digital signal with pulse width modulation to demonstrate how duty cycle and frequency changes affect the LED.